Have you ever stood at the bottom of a massive glass skyscraper on a really hot day and just wondered, how in the world does that thing stay cool? Well, we're about to pull back the curtain on the incredible hidden engineering that makes it all possible. Let's dive right in. I mean, really think about that for a second. We're not talking about some little window AC unit. We're talking about delivering thousands of tons of cooling power silently, efficiently to every single floor. The scale of it is just enormous, and the engineering behind it, it has to be absolutely perfect. So how do they pull it off? Well, the answer is this really elegant and powerful system called the District Cooling Interface. You can think of it as the hidden heart of the building's entire climate system. It's the gateway, the crucial connection point, where all the cooling power from the city meets the building's needs. And that's exactly what we're going to break down today. Okay, so imagine the city's district cooling network as this massive superhighway of chilled water, just flowing invisibly beneath the streets. The interface then is like the super sophisticated off-ramp and toll booth that connects that highway directly to our building. It makes sure that the whole transfer of energy is smooth, controlled, and, of course, accurately billed. When you get right down to it, this interface has four main jobs. First, it has to safely isolate the building from the city's network. Second, it's got to accurately meter every single bit of energy that's used. Third, it has to protect both the building system and the city's grid from any problems. And finally, it needs to precisely control that flow of chilled water. We're going to see how it does each one. And at the core of everything, I mean everything, is this fundamental physics equation. Now, don't let the letters scare you. It's actually pretty simple. It just says that the cooling energy delivered, which is Q, really depends on two main things: how much water is flowing, that's M, and how much that water's temperature changes along the way, that's delta T. This simple formula is what governs the entire system. All right, so our journey into this system begins before the water even gets inside the building, in a place called the valve chamber. You should think of this as the official front gate. It's the very first point of contact between the public utility and the building's private system. And this is the crucial part. This chamber is the legal and physical line in the sand. Everything on one side belongs to the district. Everything on the other side is the building owner's problem. It's the official handshake point, and it's all designed to meet super strict safety codes, like ASME B31.1 for piping. So inside this chamber, you've got a few key players. You have these big butterfly valves that are basically giant on-off switches for the water flow, so you can do maintenance. You've got drains and air vents for servicing the system safely. And you have pressure and temperature taps, which are like the first little checkpoints to see how healthy the incoming chilled water is. So once the water is past that front gate, it hits the energy transfer station, or what we call the ETS. Now, if the valve chamber was the front gate, the ETS is kind of like the security desk and the utility meter all rolled into one. This is where all the magic of measurement really happens. You know, the ETS really has three main jobs. First, it's the cash register. It has to measure energy use with incredible precision so the building gets billed correctly. Second, it's the traffic cop. It manages pressure to make sure the flow is smooth and stable. And third, it's an informant. It's constantly feeding data back to the central plant, helping them optimize the entire citywide cooling grid. So how does it do all that? Well, it's packed with a whole suite of high-tech sensors. It's got ultrasonic flow meters to track the exact volume of water, super precise temperature sensors to measure the change from supply to return, and pressure transmitters that monitor the system's force. All of that data gets fed into a central BTU calculator that crunches the numbers in real time for billing. Pretty cool, right? Okay, now we are arriving at what is, without a doubt, the most critical component in the entire interface, the plate heat exchanger, or PHEX for short. This is where a really clever piece of engineering called hydraulic separation happens, and trust me, it is a total game changer. Just look at this. On the left, you've got the primary loop. That's the city's water. On the right, you've got the secondary loop. That's the building's water. Inside that heat exchanger, they get incredibly close, passing heat energy between them, but, and this is vital, they never ever mix. This separation is everything. It means a problem in one building, like a leak or some contamination, can't crash the entire city's grid. It also gives the building owner complete control over their own water pressure and chemistry. So how do we know if the heat exchanger is actually doing its job well? Well, that's where this formula comes in. Just think of it like an efficiency score. It tells engineers exactly how well that unit is transferring heat, or Q, based on the temperature difference between the two water loops.
This helps make sure they pick the perfect-sized, most efficient exchanger for the job, one that meets all the key industry standards.
Okay, so theory is great and all, but let's see how this whole thing works in the real world. We're actually going to run the numbers for a typical building to see exactly how an engineer would design the system from the ground up. All right, let's say our example skyscraper needs 1,200 kilowatts of cooling power on the hottest day of the year. That's our target. That's the Q from that first formula we looked at. The entire goal of the system is to deliver this much energy both efficiently and reliably. So we take our values and we plug them right into that core formula. We know our target Q is 1,200 kilowatts, and we're designing for a 5 degrees Celsius temperature drop. With a little bit of algebra, the equation spits out our answer. We need to supply 57.3 kilograms of chilled water every single second. That's what it takes to meet the building's cooling demand. And this is why the system is so effective. What you get at the end of the day is precise, verifiable billing. You get full compliance with really important energy codes like ASHRAE 90.1. That hydraulic separation protects the city's main network while giving the building its own stable, clean water loop. And the whole thing is optimized for maximum energy efficiency. It's just a truly elegant piece of engineering. So, as we look to the future, with our cities getting bigger and our climate getting warmer, you really have to wonder, is this highly efficient, centralized, and controlled approach the key to keeping our future skyscrapers sustainable and cool? It's definitely something to think about. Thanks for joining me for this one.